Okay, good morning. Good. First of all, some of you may have just joined the class, so let me introduce myself. I'm Dr. Joseph Chen. My office is in Math Building 848. Office hours are Monday, Wednesday, Friday, 9 to 11 a.m. And email is chenjk@purdue.edu. Make a note of the course web page at the bottom, math.purdue.edu/MA261. Okay, so in case you just joined the class, that's me, and everyone else, that's still me. All right? Okay, how was recitation yesterday? Good? No? Good? All right. Okay, so we're going to move on. We're going to look at section 12.5 today. And you're going to find out that the way we cover things in 261 is very much like how you cover things back in Calc 1. We'll start by looking at simple shapes, but everything will be in 3D as opposed to just 2D. So in 12.1, we'll be looking at equations of lines and planes. Okay, so first of all, we're looking at lines here. A line is a very simple shape. To determine a line completely, we need only two things. We need to know one point on that line and in what direction this line is going. And the direction of line. Okay? Now, if you think back in the two-dimensional situation, a point, of course, is a point. The direction of the line in the two-dimensional system was given by the slope. Right? So if you know the slope and you know one point, you could write out the equation of a line, y is equal to mx plus b, for example. In higher dimension, the situation is very, very similar. In 3D, slope is not enough anymore. You can't just tell me the slope of the line is 45 degrees. Right? There's more information now. I can point my arm at the 45-degree angle, but I can swing my arm all the way around this room. I need more information as to which way I'm pointing at. And the easiest way to do that is to tell us what vector is that line parallel to. That is parallel to the line. Okay, so now we got the situation here, and then think about what the line really is. It's really nothing more than a collection of a bunch of points arranged linearly, right? I look at the seats here, this one row here, or column here. This is a line. This is a collection of a bunch of students or seats in one particular direction. Same thing here. You can tell me where the dots are. We can line them up, and we got a line. All right, so how do we do this? Let's sketch a line out here. Here's my three-dimensional coordinate system, x, y, and z. And here's my line somewhere in this space. Let's call that line L. Now suppose I know one point this line has, say right here. We'll call that P sub 0. And its coordinate is x, y, z sub 0, whatever they are. It's a number that we, in principle, these are numbers that in principle we would know, right? 1, 2, 3, 2, 3, 1, whatever. I also know the direction that this line is parallel to. So for example, let's say I know a vector on this line. And we'll call that vector v. Okay? Now to make this line here, what we're going to do is to again, remember it's a collection of points. Traced out by a vector from the origin. So for example, the point that I know, this P0 point right here, is the tip of a vector r sub 0 coming from the origin, ending right at that point. Now to collect all of these other points here, I have to start adding another vector going in the same direction as the line, determined by this, but at different lengths. Okay, so that's one point. To get another point, to get there, first I have to get onto this point, onto the line, by going to R0. And then I'm going to add another vector along the line determined by this direction. So V times whatever length I wanted to go. Okay? So this takes me to here. And T times V tells me how far to travel along this line. So if I want T to be 1, I go up to here, and then 1 times V takes me to a new point. So that new vector would trace out a different point. So let me sketch out a second point right here. P1, x1, y1, z1. Right? So this vector is the vector addition of the original vector to the P0 point plus some other vector along that line. That takes me to here. And by changing t, this value t, I can point this new vector r anywhere along this line, from here to here, any direction and any length I wanted to go. So this t here, this is called a parameter. And here, by changing the value of t, the tip of r gives a new point on the line L. So this right here, this is an equation, one way to specify a line. And not just in three-dimensional, in any dimensional world. These vectors, they're vectors. They can be four-dimensional, one-dimensional, well, no, not one-dimensional, two-dimensional, three, whatever dimension you want it to be. For us, we'll be mainly dealing with 3D, but it doesn't have to be just 3D. So this is called the vector equation. Of the line L. All right? So again, remember, you need to know one point, you need to know the direction. This tells me where that point is, coming from the origin. This tells me the direction. So here we contain everything we need to get equation of that one line. Does that make sense? Yep. It's essentially y is equal to mx plus b if you collapse everything back to the two-dimensional situation, right? One point, it could be the y-intercept, it doesn't have to be, and then the slope in a two-dimensional world. Okay, so that's the vector form. It's not always the most convenient form to work with. So let's change things a little bit. We'll still be using the same equation, but let's break it down into components. So now suppose we know that direction of that line is given by a vector A, B, C, whatever A, B, C are. And these, by the way, are called the direction numbers. Okay, so for example, if V is ABC, and everything else can be broken down into the x and y, x, y, and z components the same way. Then the vector equation we just looked at becomes vector x, y, z equal to the vector x sub 0, y sub 0, z sub 0, plus the parameter t. In many applications, this t is time, but it doesn't have to be time. If it helps you to think of it in terms of time, that's great, but it doesn't have to be. It often is, but it doesn't have to be. Okay, so I put in the components of the vectors for r, r sub 0, and v. Then the right-hand side becomes the x component of the point plus a times t, the y component of the point plus b times t, and then the z component of the point plus c times t. So in essence here, what we did is we took a vector, break it down into x, y, z, and just look at them as simple linear equation on their own. So x is determined by this, and this is your standard equation of a line, right? A point, slope. A is kind of the slope in the x direction. B is the slope in the y direction. Z is the slope in the z. C is the slope in the z direction. So we could write this as x is equal to that, and y is equal to that, and z is equal to this. It's still the same line, but now we broke it down into components. And this form is called a parametric form. Okay, the earlier form is a very compact, very condensed form, a bunch of vectors. Here, often you want to work with the x, y, z separately. So here we got things broken down into components. Okay, before we go too far with this stuff, let's do one example with a few numbers here so you get a better feel of how we get the equation out. Let's find the equation in both forms of a line that goes through the point 4, minus 7, 4. And parallel to the vector 1, 3, minus 2 over 3. Okay, so here's the picture we saw earlier. And actually, let's redraw this picture. We got everything we need here. We know one point. We know the direction this line is going. There's our line L. And the point right here, let's call that point here 4, minus 7, and 4. And remember, the vector r sub 0 is a vector going from the origin to that point you know about. So how would you write this vector? What are the three components of this vector? A vector that goes from 000 to here, how would you write it? Yeah, exactly. You start with a 0, you want to get to a 4 for x, so you need to add 4 to your original point. You start with a 0, you want to get to minus 7, so you got to take away minus 7. Same thing with z. So if you're measuring this from the origin, the vector from the origin to any point is the same as the point, but written as a vector. Remember, this is also the same as 4i minus 7j plus 4k. Tells you how much you need to move in individual components from the origin to that point. And we know this vector that the line is parallel to, which means the vector, you can think of it as part of that line, tells you the direction. Okay, so the equation in the vector form, to start with that, is the vector r equal to r sub 0 plus t times v. Think of it as y is equal to mx plus b. It's exactly the same thing. 1 point plus direction times whatever parameter you want it to be. Okay, so we got 4 minus 7, 4, plus t times v, 1, 3 minus 2, over 3. And most of the time you want to put these two vectors together. 4 plus 1t in the first component, minus 7 plus 3t in the second component, 4 plus minus 2 over 3t in the last one. All right, so there's our vector form of that equation of a line. So notice that if you're given this equation here, looking at the numbers that don't have any t attached to them tells you that one point that you know, 4 minus 7, 4. That's that one point. And the coefficients of t in each place is the direction of the line. Essentially the slope in each direction. Does that make sense? Questions on this form here? Good. So that's the vector form. That's very simple. The parametric form is just the individual components listed out. All right. So parametric form is the x component is 4 plus t. Y component is minus 7 plus 3t. And the z component is 4 minus 2 over 3t. And in this way, if you just want to track x for some reason, then you can basically ignore y and z. You can just see how x is going to grow as time goes on, and how y is going to change, how z is going to change. All right? There's one last form we haven't looked at. This form is called a symmetric form. And the easiest way to get a symmetric form is to start with a parametric. So we'll leave that in general here. X is x sub 0 plus at. Y is y sub 0 plus bt. And z is z sub 0 plus ct. The idea is to eliminate t from this. So for example, notice from the first equation, the first equation tells me that t is equal to x minus x sub 0 over a. Right? Subtract this over, divided by a, then it gives me that as a t. The second equation tells me something very, very similar. Same thing with the last equation. Oops, sorry. All right, so in each equation I solve for t, and all of these things are equal to the same variable t. That means this must be equal to that, equal to that. So we write it this way. So right here, this is kind of an unusual looking equation, but this is what's called a symmetric form of the equation. Symmetric because if I give you a value of t, you will be able to find out x, y, and z, right? So all of these things are equal. Basically, the rate of change of x divided by its slope in some way is equal to the rate of change of y divided by its slope, and so on. So there's a symmetry in some sense. And as an example, let's find the symmetric form of this line right here. From x equation, I see that t is equal to x minus 4. From the y equation, I see that y plus 7 over 3 is equal to t. And the last equation here, z minus 4 over negative 2 over 3 is also equal to t. And now all three of these things are equal. So therefore, the symmetric form can be written as x minus 4 is equal to y plus 7 over 3 equal to negative 3 over 2 times z minus 4. So right there is the symmetric form of the same equation of that line, the same line. Does that make sense? Questions on these three forms? Okay, now let me ask you a question. Looking at the symmetric form here, what if at least one of these three numbers, a, b, and c, is equal to 0? We can't write it out this way anymore. Suppose a is 0. Then this is not going to make much sense, right? So what does it mean if a is equal to 0, for example, but b and c are not equal to 0? What do you know about x if you know a is equal to 0? It's a constant, right? So in case of one of these being 0, that tells you that variable must be a constant. Okay, so if a, b, c is 0, then that particular variable is constant. Okay, so if at least one is a 0, then that particular variable is a constant. In that case, for example, if a is equal to 0, but b and c are not equal to 0, then in that case, you would write a symmetric form this way. You leave the constant guy on its own, x is equal to x sub 0, the point, the x component of that point on the line that you know. The other two, you can still relate them by the same parameter t. So you relate the other two the same way, like a standard symmetric form. But you just leave out the constant variable on its own. Make sense? Okay. Let's do one more equation, one more example with a line, and then we'll look at the planes. Find the symmetric form of the equation of the line segment from the point 4, -4, 8 to the point 8, 3, 7. This is equivalent to saying find the equation of a line between 2 points. You did problems like that with a two-dimensional line, right? You give you 2 points, you can find the slope, and you can find the equation of the line. Same thing here. We still need the same thing we needed before. We need 1 point, which we have actually 2, and we need the direction of that line. So here, actually, the only part of the line that we want is this part. We want to know specifically the line segment, not the entire line anymore, coming from here to here. All right, so let's start with the vector form. And you can let either of these points be the original point. It really doesn't matter. So here I'm going to let this one be the original point. And therefore, the vector going from the origin to that point is just that point, but written as a vector, 4i minus 4j plus 8k. What about v? How would you find v? Yeah, the vector going from here to here, right? So the difference of x, y, and z, that's the vector. Very, very good. So there we go. We need 4. This is 7, right? And then -1. Right? So here we go. So therefore, my vector form is very simple. Four, -4, 8 plus t, 4, 7, minus 1. Or 4 plus 4t minus 4 plus 7t, 8 minus t. And notice, if t is 0, obviously this part goes away, so we're at here. But notice that if t is equal to 1, 4 plus 4 is 8, minus 4 plus 7 is 3, 8 minus 1 is 7. When t is equal to 1, I'm at this point right here. So because we only want the line segment, I have to specify the range of t. 0 puts me here, 1 puts me here. If I vary t somewhere between 0 and 1, I can collect all the other points on this red line segment. So that's the vector equation. Okay? Questions? Yeah. If you find the vector the way we just did, then it's always going to be between 0 and 1. But of course, you can find it. You just need one vector. It doesn't matter how long it is. So you could specify the vector by a unit vector if you want. In that case, t will be something other than 1 at the very end. But for convenience, I think leaving between 0 and 1 is probably the most convenient way to do things like that. Okay, now let's get to the symmetric form. So first we start with the parametric form. So there's the parametric form. To get to the symmetric form, we just solve for t and put all of them equal to each other. So here, t is equal to x minus 4 over 4. It's also equal to y plus 4 over 7. And it's also equal to z minus 8 over negative 1. So there's our symmetric form. Okay, as you can see, the vector form is always the easiest one to start with. And going from vector to parametric and then symmetric is a very, very straightforward process. Put together the line the usual way and go into whatever form that you want. Obviously, implied in here is that t is somewhere between 0 and 1. Yeah? Because t is not there anymore, normally we don't need to specify the range of t. It's not something we track anymore. Here we're actually tracking the relationship between the three variables. If I know one of them, can I find out the other two? That's essentially the purpose for that form. We kind of want to ignore t. Okay, so that's line. Let's look at plane. Now imagine I have a plane, and right here, think of the floor of this room as the plane we're looking at. If I can find a vector, let me call that vector n, that is perpendicular to the plane. So, like me, for example, I could be that vector n in relationship to the floor of the room, right? I'm perpendicular, more or less, to the floor. So this vector actually is perpendicular to every other vector that's on the plane. Perpendicular to every vector contained in the plane. Okay, so if I know one point on this plane and a vector that is perpendicular to that plane, then this vector is going to be perpendicular to every other plane that's contained, every other vector contained in that plane. In other words, the dot product of this vector n with every other vector is going to be 0. Yep. So n dot the vector going from here to any arbitrary other point x, y, z. Is going to be 0 at all times for whatever value x, y, and z. So I forgot to specify here. Is a point the plane goes through. So to put together equation of a plane is very, very similar to equation of a line. You need one point, and you need a vector, but this time you need a vector that's perpendicular to the plane as opposed to parallel to a line. But otherwise, it's exactly the same idea. You just do a dot product. If the vector A is given by A, B, C, then this equation right here is ABC dotted with x minus x0, y minus y0, z minus z0 equal to 0. Or you can write it this way, a times x minus x0 plus b times that. This is how we do dot product. C times z minus z sub 0 equal to 0. And what I got in a box right here, this is the equation of that plane that contains this one point and has a vector that's perpendicular to the plane defined by the direction numbers A, B, and C. This is called a scalar form of equation of that plane. This right here is the vector form, often not as useful as the scalar form. All right, so one example with this stuff. Equation of the plane through the point 1, 2, 3 and orthogonal, which means perpendicular, orthogonal to the vector minus 2, 4, minus 1. Again, like I said, very similar to a line. If you know one point, you know a vector that this plane is perpendicular to, as opposed to parallel to a line, then you can put together the equation. Okay, so a very rough schematic here. This is what's going on. Here's the point, and from that point, I draw my vector minus 2, 4, minus 1. And that vector is going to be perpendicular to every other vector that's contained in that plane. So suppose some arbitrary point x, y, z is over here. Then n dotted with this vector will give me a 0. because they are perpendicular to each other. Okay, so n dotted with this vector, starting from 1, 2, 3 to go to x, y, z. That vector can be specified as x minus 1, destination minus the origination, at destination minus the original, destination minus the original. And we know because they're perpendicular, when I dot the two vectors, I get a 0. So this becomes minus 2, x minus 1, plus 4 times y minus 2, minus 1 times z minus 3 is equal to 0. If we multiply everything out and simplify a little bit, we end up with this equation. That's a positive 2 minus 8 plus 3. So that's a, in the end, we end up getting a 3 here. So this right here is the equation of that plane. Okay? It's not a vector. Notice this is not a vector. A line starts with a vector form of the equation. The equation of a plane is never a vector. Right? Because a plane really doesn't have any kind of direction except this normal vector, which you can see is the coefficient of x, y, and z. Okay, one last thing before we go. Suppose I got this plane right here, and I know 3 points on this plane. And I asked you for the equation of that plane. How would you approach that? Yeah. Right, exactly. So we need a vector that's normal to the plane, perpendicular, right? So let's say this vector is, we'll call that u, and call this vector v. And you know how to find u and v. So you start with n is equal to u cross v. Can I do v cross u? Is v cross u also perpendicular to that plane? Yeah. Or v cross u. How are these two things related? They're negative of each other. If I know this one, then this one will be the negative of that. So one will point straight up, one will point straight down, right? So that's my normal vector, 1, 2, 3. And then I need 1 point. I choose any of these 3 points to be the point I work with. Then I use any point as the x0, y0, z0. And then I can put together my equation. It'll turn out to look like that. All right? Okay, that's it for today. See you Friday.